Okay, I'm going to start because we have a lot to deal with. The slides are available online, and I've hidden some slides in order to get more quickly to the main meat of this section, which is the temporalized relations in the OWL version of BFO. So in the common logic version, we don't need temporalized relations because we can have multiplace relations to our heart's content. So this is Alan. You can see that he's somewhat fuzzy at this time of day, so he didn't manage to wake up in time, so I will present his slides. This is a summary of what BFO-ISO brings, which we didn't have in BFO-2. So most importantly, we have not merely an OWL version. Actually, we're going to have two OWL versions, as we will see, but also a first-order logic or common logic version. So I will go backwards and forwards between first-order logic and common logic, but for BFO purposes, it's the same. We're not using any parts of common logic which are not already part of first-order logic. And having the first-order logic axiomatization gives us a clear basis for evaluating criticisms of BFO, both in OWL and in natural language. So now we can point to something and we can actually prove things to be either true or false or inconsistent. So the temporal theory in BFO is extended, first of all, at the level of the textual artifact. In other words, the labels, the terms, and the relational expressions and the definitions. And I've mentioned this already, that we have two new terms, temporal instant and temporal interval. And now we have two new relations, first instant of and last instant of, which the range of both of them is temporal instant, the domain of both of them is temporal instant and the range is temporal region. Then we have a new temporalized relation called concretizes at. So we found it necessary to temporalize concretizes. I'll explain why. And then we have a new relation of is carrier of, which has to do, for instance, with the information bearing phenomenon, which again we'll come to later. And all relations now have inverses, including these relations. And we have split the part of relation into a binary, a current part of relation, and a time-indexed continuant part of relation. And that's where the primary innovation is, because you can't do time indexing in OWL. We do a sort of time indexing in OWL. This is the picture of how spatiotemporal relations work. And I'm not going to go into this in detail, but you can download the slides and study it for yourself. So processes occupy spatiotemporal regions, for instance. And spatiotemporal regions temporarily project onto temporal regions. And we can say things like this entity exists at a certain spatial region, or a certain temporal region. Instance of is partial. What this means is that if we say that X is an instance of some universal U at T, then that just means it's an instance at least at T. It may be an instance for longer time regions. And so on. So you can work out the meanings of these other things for yourselves. We've added a lot of temporal indexes, as you will see, but some relations we found should not be time indexed. And that's true of inheres in and its inverse, which is bearer of. It's true of realizes and its inverse. And it's true of specifically depends on, which we didn't define an inverse for because it doesn't correspond to anything lexicographically useful. And the rationale for not having these things temporally indexed is presented here. The rationale for wanting these not to be temporally indexed is that it makes modeling easier. So the fewer axioms we need to capture in the model, the easier it is to build the model and thereby prove consistency. Now concretizes, on the other hand, was in BFO-2 without a temporal index. Concretizing is the relationship between the information content entity Barack Obama is no longer president and some ink patterns on a piece of paper which say Barack Obama is no longer president. So the ink patterns concretize the information content entity. And now the way it works here is, and this is why it needs a temporal index, we have an aggregate of people which form a pattern, a shape, a quality, which concretizes the logo, which is all over the stadium printed on big flags. So the very same logo is concretized in multiple different ways. Now when the people start to move around, they may concretize a Mickey Mouse image or something. And then they move back and they concretize the big T once again. So this proves that concretizing has to have a temporal index, this Texas example. Now one interesting feature which we realized only in working out the axioms for the first order logic representation is that some object aggregates can still exist even though they are reduced to a single member. So if you have a small village fire brigade and 4 of the 5 members all resign, the fire brigade still exists, even though it only has 1 member. So the organization, which is the fire brigade, still exists even when it's reduced to 1 member. And this, we have axioms which make this work, which is very useful for various purposes. And then processes exist at least on an interval. So there are process boundaries which exist on an instant, but processes are always more than an instant. One specifically dependent continuant can adhere in more than one independent continuant, and they're called relational. So relational qualities inhere in more than one thing. Something like hate or love is a relational quality. Now let's talk about the axiomatization. So I think you all know what an axiomatization is, and it can be expressed in different syntaxes. We give you both the first order logic, old-fashioned syntax, and the common logic syntax at this address here. So that's where you find all the formal content of BFO-ISO. And you can model it, you can build a model, and the model may be completely artificial, or it may be an intended model. It may look like the real world. But it has to be a model which is in some sense satisfying, and it has to be able to tell you that your set of axioms is consistent, because if you build a model, then you prove that it's consistent. And then the model may help us also to justify adding assertions to OWL. All right, so features of the BFO first order logic axiomatization. So we want it to be useful, and we think you'll find it useful when you look at it. It tries to make explicit, implicit things which were in our minds perhaps when we were building BFO, but which we never needed to write down because we couldn't write them down in OWL because OWL is not expressive enough. It clarifies things which were underspecified previously, and so on. And it makes sure that we have a consistent theory because we have models. And there are now tools for using first order logic artifacts. You can't prove first order logic artifacts are consistent, for instance, just by using tools, but there are tools which will help you build a proof manually. But there are tools which will help you do other things as well, which didn't exist just a couple of years ago. And finally, we can use it to help build BFO-OWL. And so we built two normative versions of BFO-OWL. All right, so we start off with the first order logic axiomatization. I've gone through this. So the idea is, if you embrace BFO, then you see the world through BFO spectacles. And this is a good thing because there are hundreds of other people who see the world through BFO spectacles. And so if, like Alan, you have a career as a data scraper, which means you go to the internet and you find some data about protein molecules, and you want to capture this data and turn it into structured knowledge, as it were, then you want the way you capture this data to be interoperable with the way this gentleman over here captures that data. And if you're both viewing the data through BFO spectacles, you're more likely to build a representation of heterogeneous data in ways which are still consistent. And that was why Alan became involved with BFO, because he found that it helped him do his data scraping. And so we're going, for purposes of building BFO in OWL, we're going to take the first order logic axioms as authoritative, and then we're going to surely extend those axioms in the future, but for the moment we treat that set of axioms as authoritative, and then we use those to build the OWL version. And I don't think I need to go through this. So when building the OWL, we're not interested in OWL data expressions. We're not interested in annotation properties. We're just interested in capturing the content of BFO. Now we have, it's well known that you can translate any OWL artifact into a first order logic artifact. It's a trivial matter. But what we did was we documented a well-defined translation from BFO in OWL to first order logic, which is not trivial. And what we needed to do was to create within the first order logic counterparts of the BFO OWL expressions, and then associate those with extra axioms in the first order logic with first order logic predicates of a simpler sort. So this is documented in the files at the link at the bottom of the page. Now, we could prove soundness. What that means is that you can't infer things which would be recognizably wrong from a BFO perspective. And we could not prove completeness, which is good, because we don't want to claim completeness. We don't want to claim that BFO covers everything in reality, because we know that there are things that we haven't yet covered. So, BFO OWL specifically should be sound, but it may not be complete. And we could show soundness using RDF reasoners. And it goes like this. We show soundness indeed by going through the first order logic, for which we have a proof of consistency, and then we show that we can translate each assertion in OWL, in BFO OWL, into a corresponding assertion in the first order logic axiomatization. And we can then use the OWL reasoner to create the left-hand column, and we can show that the right-hand column exists in the first order logic prover as applied to the BFO first order logic axiomatization. So, and that is the same thing with going down through the OWL side and then trying to prove that what we find by going down through the OWL side holds also on the first order logic side. So this is about how we validate soundness and how we validate that in other words, how we validate that every OWL assertion of BFO is provable from the first order logic axiomatization. And now we move on to temporal regions. So we have lots and lots of assertions involving the use of time-indexed relations. So parthood, location, participation. A thing is at place 1 at time t1, as it at place 2 at time t2. We want to capture such assertions, but they involve three-place relations, and we cannot use three-place relations in OWL. We're restricted to two-place relations. What do we do? Well, we first of all need a theory of temporal relations and of temporal instants and of temporal intervals. And we need a logic governing those things, which we use minimal extensional Mariology for time instants and time intervals. And we want to be able to quantify over both of those, which means over temporal regions in general. Now, there are various common choices in temporal theories. So some people hold that time is dense. Some people hold that it's made of time quanta, so it's discrete. Some think it extends forwards and backwards infinitely, and BFO doesn't make any assumption of that sort. Now, that's good, because it means we're not tied to any assumption of that sort, which means that we're more general, but also it means that we can allow finite models, because we don't make an assumption of denseness, and if we did, we'd only be allowed to have infinite models. Infinite models take a long time to build, and so if we can build a finite model, then that is very useful. All right, now this is how it looks. This is a temporal region. The temporal region has gaps. It contains an isolated point and certain time intervals. It has a first instant and it has a last instant. We do not assert that the first instant or the last instant is always a part of the region, but every region has a first instant and a last instant. And there are zero-dimensional regions which have more than one point in them. We went through this before, and there are non-connected one-dimensional temporal regions. But now we introduce the terms time instant and time interval to capture connected zero and one-dimensional regions. And the temporal region as a whole is a disjoint union of zero and one-dimensional regions. So they are the only kinds of temporal regions that we allow. And so there is always an interval which covers all of the times of any temporal region, however gappy or complex it might be. So we can always fit any region into a temporal interval which doesn't have gaps. All right, now we come to the pièce de résistance, as we say in English. So this is where we start dealing with temporalized relations in OWL. So OWL supports only binary relations, so ISA is easy. ISA is a relation between universals or types. It doesn't need a time index. In the paper from 2005, Relations in Biomedical Ontologies, we put forward a pattern for how to do ISA. In other words, how to do A as a B, or A as part of B, where both A and B refer to classes or universals. And the idea was that we quantify over instants of time and over instances of the universals. So to say that A is part of B is to say that all instances of A at any time are parts of some instance of B at that same time. Okay? And we use that template for all temporalized relations between classes, between universals. Now for occurrence, we can drop the time index. We only need to pay attention to the time index for continuance. So the Second World War was part of the collection of all events in the 20th century is true atemporally. It will be true in 1,000,000 years. But my pimple on my cheek is part of me is true only for the time when I have this pimple on my cheek, and it will not be true in 100 years or in 2 years maybe. So it's only for continuance that we have to worry about temporalization. Occurrence are such that assertions about them are true atemporally. All right. So that failed. So the account we gave in the paper on relations in biomedical ontologies, which made everybody very happy for about 10 years, made Alan very unhappy one day when he realized that it didn't work. And the reason it didn't work is because it could be true that every A at every time, it could be true that A is part of B in the sense that every instance of A is part of some instance of B at every time, but it's not the same instance. And that makes it problematic because in some cases, for instance, you have to have some molecule in your skin of a certain chemical type, but it's not the same molecule which fulfills that need at different periods in your life. So it's true that you need a molecule of this kind at every point in time at which you exist, but it's not true that it has to be the same molecule. And the way we formulated that is consistent with it being the same molecule, and that is not going to work. That's going to cause problems. All right, so the axiomatization strategy is we're going to develop binary relations, but we're going to be much less ambitious. We're not going to try and develop binary relations at time instance. We're going to temporalize binary relations, not by having instants of time or points in time or even specific regions in time, but rather by using the phrases at some time and at all times. All right, so the original relation might be occupies spatial region at, and then the temporalized relations will be occupies spatial region at all times and occupies spatial region at some time. These are both binary relations, but they're temporalized. So we have solved at least part of the problem of capturing the temporal nature of relations between continuants. And it looks like this. So the black here is what we originally had, the black and the green. We now have also the red. The red means that we always specify when we're dealing with temporal relations, whether we're dealing with them as holding at all times or at some time. Now these are the relations which we have temporalized in this fashion. And this includes all the inverses. So all of these now exist in the temporalized version of BFO-OWL, in addition to the current relations which don't need temporalizing. All right, now the benefits of this is that we can use time index relations. We can now capture a lot of what's involved in the relations between continuants, which involve time, which we couldn't capture at all in the logically coherent way before. All of the assertions in this new OWL version are provably consequences of the BFO first order logic. But we still can't do everything, so that's what this says. We don't need to go through this in detail. We're working on developing conservative extensions of BFO that will allow us to do some of the things that we wanted to do and which we can't do, even on the basis of these new relations. All right, so I'm going to go through the temporal quantification again more clearly, I hope. This is what we had originally. To say that C is part of C1 means for all C and T, if C holds of C, big C at T, then, if C is an instance of big C at T, then C1 is such that there is some instance of C1 which it's part of at T. And he shows that you can generate a contradiction from that. And that's another version of showing what... I'm not going to go through this because we don't have time. So this is the revised pattern. This is what we had before, and this is what we have now. So what this says is that instead of saying for all classes big C, big C1, big C is part of big C1 means that for all instances of big C, at all times T, C being an instance of big C at time T means that there exists some time T prime which is part of T and which is such that at that time T prime, C1 is an instance of big C1 and little c is part of little c1. So that sounds really annoying in English, but you can read it. So, in fact, I'm not sure why I read it out loud. Anyway, that solves the problem. That means that we can now capture relations between classes which involve time. In other words, relations between continuant classes in a logically safe way, which we couldn't do before. All right, so as I said, all the formal content of BFO in the new ISO version will be available on the ISO maintenance portal, publicly free for use, and it's already there if you want to look at it now. And you can find these slides at this link if you want to look at the details which I left out in presenting Alan's work on OWL and first order logic. And I didn't do a very good job with Alan's work, but I did my best. All right, any questions? Yes?
What about object aggregates that have no members at some time?
They don't exist.
So
And then
the object aggregate can exist, not exist.
yes, so that's a philosophical question. So if you have a watch and you take your watch to the repair shop and the repairman takes it apart and then you go back for it a week later, is it the same watch or is it a new watch? I don't want to answer philosophical questions.
But in some cases you would have maybe documentation about, in an organization.
Exactly, yes. Actually, so yes, good. Yeah. Yeah. So, you're exactly right. The guarantor of the existence of positions in an organization when people go on holiday, for instance, is the documentation which underlies the way in which the organization is structured. So there is some part of the organization, taken more broadly, which survives losing all its members, which is the documentation. And I think that we have to go down that sort of road if we're going to do justice to what happens when people go on holiday and so forth. Dying. Yep.
Again, on the extraction of the old version from the common logic one, there is this strategy of for temporalized relations that obviously you use explicitly. Do you have a measure of how much of the common logic version or the first order logic version is lost in the translation?
No, but we do have a measure of utility of what we have now. So in the biological world, there are certain common examples where we have to have temporalized relations for continuance. So they're primarily in the area of development. So babies lose teeth, for instance. And there are many, many axioms about different stages in the development of different organisms. So it's primarily for developmental biology that this kind of temporalized OWL is needed. And if you try and think, so the question is this useful? The answer is that it is useful because it's nearly always the case that we can capture nearly everything we want to capture using at all times. And then we can have transitivity. That's the important thing. It's very hard to find a case where A is part of B at all times at which A exists, and B is part of C at all times at which B exists, but it's not the case that A is part of C at all times where C exists. So there are a few, but they're very, very weird. So what this means is that we can capture nearly all the examples that we want to capture in this way, and we couldn't capture them in the old way.